Hello friends, welcome to John Lewis NEET Chemistry channel. Let's see question number 12 from Haloalkanes and Haloarenes chapter. Which of the following biphenyls is optically active? Okay, first of all we need to know what is biphenyl compounds. So there should be two benzene ring bonded to each other. So this is one benzene ring and this is another benzene ring. So they are bonded together and therefore it is called biphenyl. So this type of compounds are optically active under two conditions. See, in fact, they do not have any chiral carbon because every carbon is having a double bond. Therefore, there is no chance of a carbon bonded to four different groups. Therefore, there is no chiral carbon. Yet, they exhibit optical isomerism. How? See, in biphenyl compounds, there are two conditions to be optically active. So, the first one is both the benzene rings should be substituted in the ortho position. See, they should be ortho substituted. One thing. Then second thing, whatever is substituted in the ortho position, they should be unsymmetrical. It should be unsymmetrical. Okay, now first let us see these two conditions here. See, for first benzene here, so this is a bond connecting these two benzene ring. Therefore, this is the ortho position. This is also the ortho position, two ortho position. So these two should be substituted. So here A and B, let us see. And similarly for the other benzene ring, so this is a bond connecting the two benzene ring. Therefore, this and this are the ortho position. So here also it should be it should have substituents. So let us say it is C and D. It is having C and D. Okay, that's fine. Now, so if you divide this compound into two along the axis which is connecting the two benzene ring. So this is called achiral axis because there is no chiral carbon, but yet it exhibits optical activity. So this axis is called achiral axis. So it is not having four different groups bonded to it, but still it is optically active. Therefore this axis is called achiral axis. So if you divide the benzene like this into two halves, that A and B should not be the same. A and B, the two substituents in the same benzene should not be the same. Similarly, the other benzene ring in the ortho position, what is substituted? C and D are the substituents there. These two should not be the same. They should not be the mirror image of each other. So that is why we have written unsymmetrical. That is very important point. Okay. Then how can it be? See, they are in the if they are in the same plane, it may not be optically active. See here, both the benzene rings are ortho substituted. Therefore, when the big ortho groups are there together, there will be steric hindrance. Therefore, in order to minimize that, what will happen? One benzene ring will turn vertically. See here, one benzene ring will be horizontal like this. And the other benzene ring will turn into vertical like this. So they turn vertical. So one will be along the plane and the other one will be vertical like this. They will be perpendicular to each other. So they are now they are not having plane of symmetry. So they are in different planes now. This is horizontal and this is vertical. That will be different. Why? Due to the steric hindrance in the ortho position, they twist so that the repulsion is minimum. When it will be minimum? When they are 90 degree apart. That's why one is horizontal, the other one is vertical. So now they are out of symmetry. So therefore it exhibits optical isomerism. Now with this explanation, with these conditions, let us see one by one now. You take option A, there is a substituent here, there is no substituent here. So we can omit this one. And second one, no substituents here anywhere in the ortho position. So we can leave it out. And here, in both the ortho position, there are substituents, but these two are same. And in the other one, there is no substituents. Therefore, this also cannot exhibit optical isomerism. Therefore, without checking anything, we can say option D is the correct one. But let us check whether it obeys all these conditions here. See, in the ortho position, there are substituents. Okay, these two are different, fine. And similarly, the second benzene ring also in ortho position, there are two substituents. And when you divide this, they are not mirror images. They are unsymmetrical. And therefore, what will happen here? So the bromine and bromine will repel each other. Iodine and iodine will repel each other. Therefore, one of the benzene will appear vertical. The other one will be horizontal. So they will be 90 degree apart. So therefore the plane of symmetry is also not there, therefore it will be optically active. Hope everything is very clear. So I repeat one more time, in biphenyl compounds there need not be any chiral carbon. But what are the conditions to be optically active? In both the benzene ring, ortho group should be substituted. In each benzene ring, the ortho substituent should be different. Okay, then what is the second condition? So that is what is unsymmetrical. Then there should not be any plane of symmetry. So in the ortho position, there will be repulsion. That will be automatic now. When both the benzene rings are substituted in the ortho position, due to steric hindrance, it will twist itself so that the strain is minimum. So automatically they will be out of plane. Okay, so therefore compound D is the correct answer. Please click thumbs up, comment, share and subscribe to my channel without fail. Thank you very much for watching. Until we meet next time. Bye bye.